Tonight, we're going to explore worlds that shouldn't exist. Planets where glass rains sideways at thousands of miles per hour. Where the surface is hotter than the sun itself. Where entire atmospheres are being torn away into space. These aren't imaginary nightmare worlds. They're real planets, orbiting real stars, discovered by our telescopes in the last 2 decades. And they're so extreme, so completely hostile, that they force us to rethink everything we thought we knew about how planets can exist. By the end of tonight, you're going to understand why these worlds are so terrifying and what they tell us about the universe we live in. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. For most of human history, we only knew about the planets in our own solar system. 8 worlds orbiting our sun in what seemed like a predictable pattern. Mercury, Venus, Earth, Mars in the inner system. Small, rocky, baked by the sun's heat. Then, Jupiter, Saturn, Uranus, Neptune in the outer reaches. Gas giants, massive and cold. This arrangement made sense. Rocky planets, close to the star, where only heavy materials could survive the heat. Gas giants, farther out, where it was cold enough for hydrogen and helium to gather. We thought this was normal. We thought all planetary systems would look like this. We were wrong. The universe is far stranger than we imagined. Imagine a planet where it rains glass, sideways, at 4,500 miles per hour. This is HD 189733b. A real planet orbiting a real star, 63 light-years from Earth. HD 189733b is roughly the mass of Jupiter, but orbits terrifyingly close to its star. The planet completes one orbit every 2.2 days. A year on this world is shorter than a weekend on Earth. The planet is moving at incredible speeds, roughly 90 miles per second, just to stay in orbit. From the surface, the star would race across the sky, sunrise to sunset, in only a few hours. The star itself would appear huge, dominating the sky, filling your vision. Like most planets that orbit this close to their stars, this planet is tidally locked. One hemisphere permanently faces its star, baking in constant light and heat. The other hemisphere faces away into eternal darkness, never seeing the star, never experiencing sunrise, locked in permanent night. The dayside temperature reaches about 1,700 degrees Fahrenheit. Hot enough to melt most metals. Hot enough to vaporize water. Hot enough that the atmosphere itself glows. The night side is cooler, around 1,000 degrees Fahrenheit. This temperature difference, this gradient of 700 degrees across the planet, drives winds of extraordinary speed. The atmosphere on the day side gets superheated and expands. Hot air rises, creating massive low pressure. On the night side, cooler air sinks, creating high pressure. The pressure difference forces air to rush from night side to day side at low altitudes, from day side to night side at high altitudes. A permanent circulation pattern locked in place. Scientists have measured wind speeds at over 4,500 miles per hour, faster than any jet aircraft, faster than most rockets. These winds would rip apart any structure we could build. The force would be like being hit by a continuous explosion. But the winds aren't the strangest part. The strangest part is what's in those winds. The atmosphere contains silicate particles. Silicon and oxygen bonded together, the basic components of sand and glass. On Earth, silicates exist as rock, quartz, granite, feldspar. But on HD 189733b, the temperatures are hot enough that these materials don't stay solid. On the hot day side, silicates exist as vapor mixed into the atmosphere. The rock has evaporated, becoming gas, floating in the air like water vapor in Earth's atmosphere. But as the winds carry this vapor toward the cooler night side, the temperature drops. Not below freezing, but below the condensation point for silicates. The vaporized rock condenses. It forms tiny particles, droplets of liquid silicon and oxygen compounds. As it cools further, these droplets solidify. They become tiny particles of glass, microscopic shards, each one only a few microns across. But there are billions of them, trillions of them. The entire night-side atmosphere is filled with these particles. And because the winds are moving at thousands of miles per hour, these glass particles are carried horizontally across the planet. It's not raining down, it's raining sideways. Each particle is small, but at these speeds, each one carries tremendous kinetic energy. Each particle would strike with the force of a bullet, millions of them every second, hitting from the side, never stopping, never slowing. The landscape itself is constantly sandblasted. Any mountains, any rock formations, anything solid is worn down by the relentless bombardment. Smooth surfaces develop, polished by continuous abrasion. Sharp edges round off. The entire planet is shaped by this wind, this glass rain, this endless assault. And we know all of this because we measured it. Scientists detected this phenomenon by measuring light passing through the planet's atmosphere as it transits in front of its star. When HD 189733b passes between its star and Earth, some starlight passes through the planet's atmosphere before reaching us. By analyzing this light with spectroscopy, scientists determined what's in the atmosphere. They found signatures of silicate particles scattered throughout. The particles absorb and scatter light in specific ways that reveal their composition and size. The measurements showed these particles concentrated on the night side, where they condense out of vapor. The day-side atmosphere is relatively clear because silicates are still in vapor form. The night-side atmosphere is hazy, thick with condensed glass particles. We know the wind speeds from spectroscopy too. By measuring the Doppler shift of gases moving around the planet, scientists calculated how fast the atmosphere moves. The data is precise. HD 189733b has glass rain driven by supersonic winds. And it's not alone. This planet is part of a class called hot Jupiters, gas giants that orbit terrifyingly close to their stars. Before 1995, we didn't know these existed. For most of human history, we only knew about planets in our own solar system. 8 worlds orbiting our sun in a pattern that seemed orderly and predictable. Mercury closest in, then Venus, Earth, Mars, the rocky planets, small and dense, baked by the sun's heat. Then a vast gap filled with asteroids. Beyond that, the gas giants. Jupiter, massive and distant, taking nearly 12 Earth years to complete one orbit. Saturn, with its spectacular rings, even farther out. Uranus and Neptune, in the cold outer reaches of the solar system. This arrangement made sense. The rocky planets formed close to the sun, where temperatures were high enough that only heavy materials like iron and silicates could condense. The gas giants formed farther out, where it was cold enough for ices to form. for light gases to stick together. This is how planetary formation works. A young star is surrounded by a disk of gas and dust. Close to the star, only the heaviest materials survive. Farther out, water ice can form. Even farther out, methane and ammonia ices can exist. Planets grow from these materials. Small, rocky cores close in. Large, icy cores farther out that can capture massive atmospheres of hydrogen and helium. The final arrangement reflects where different materials could exist in the disk. We thought this was universal. We thought all planetary systems would follow the same pattern. Rocky planets close, gas giants far. It made physical sense. It matched our observations. We had no reason to think otherwise. Then, in October 1995, astronomers Michel Mayor and Didier Queloz at the Observatory of Haute-Provence in France announced something that didn't make sense. They'd been using a technique called radial velocity to search for planets around other stars. The method is clever. A planet doesn't just orbit a star. The star also orbits the planet. More accurately, both orbit their common center of mass. If the planet is massive enough, this causes the star to wobble slightly. As the star moves toward us, its light shifts toward the blue end of the spectrum. As it moves away, the light shifts toward red. By measuring these tiny shifts in the star's spectral lines, you can detect a planet you can't see. You can calculate its mass, its orbital period, its distance from the star, all from wobbles in starlight. Mayor and Queloz had been studying a star called 51 Pegasi. It's about 50 light-years from Earth. A sun-like star, slightly older than our sun, but similar in mass and temperature. They detected a wobble, a regular pattern repeating every 4.2 days. At first, they thought it must be a mistake. 4.2 days was impossibly short for a planetary orbit. Even Mercury, the closest planet to our Sun, takes 88 days to complete one orbit. A planet orbiting in only 4 days would have to be incredibly close to its star, so close that the heat should destroy it. They checked their data repeatedly. They ruled out other explanations. Stellar pulsations that might mimic a planet's signal, sunspots rotating with the star, instrumental errors in their spectrograph, all eliminated. The signal was real. They announced their discovery in October 1995. They called it 51 Pegasi b, a Jupiter-sized planet, roughly half the mass of Jupiter, orbiting its star at a distance of only about 4.6 million miles. Mercury orbits our Sun at about 36 million miles. 51 Pegasi b was orbiting almost 8 times closer than Mercury. At that distance, the orbital period was 4.2 days. The planet was moving at roughly 90 miles per second just to stay in orbit. The temperature on the planet was estimated at around 1,800 degrees Fahrenheit, hot enough to melt lead, hot enough to vaporize water. This made no sense. Gas giants form far from their stars. You need cold temperatures for hydrogen and helium to gather. You need ices to build the solid core that can then capture gas. None of this can happen close to a star. The heat would prevent it. So either our understanding of planetary formation was completely wrong, or something very strange had happened to this planet. The scientific community was skeptical. Some astronomers suggested it might not be a planet at all, maybe a brown dwarf, a failed star, maybe something else masquerading as a planet in the data. Maybe the measurements were wrong, but within months, other teams confirmed the discovery. Jeffrey, Marcy, and Paul Butler at San Francisco State University had been conducting their own planet search. They turned their telescopes toward 51 Pegasi. They measured the same wobble, the same 4.2-day period, the same mass for the planet. It was real. And as more surveys began searching for exoplanets using radial velocity, they started finding more of them, more gas giants in impossibly close orbits, more planets with orbital periods measured in days, more worlds being baked by their stars. Within a few years, dozens of hot Jupiters had been found, and scientists had to figure out how they got there. The answer is planetary migration. Planets don't necessarily stay where they form. When a planet is embedded in a disk of gas and dust, that gas creates drag. As the planet orbits through the disk, it experiences resistance. Not much, but enough to matter over millions of years. This drag causes the planet to lose orbital energy. When a planet loses energy, it spirals inward, closer and closer to the star. The process continues until the disk dissipates. The gas is either accreted onto the star or blown away by the star's radiation. Once the disk is gone, migration stops. The planet is left in whatever orbit it happened to occupy. For hot Jupiters, that orbit is terrifyingly close to the star. These planets formed far out where Jupiter formed in our solar system. Cold regions where gases could condense. They grew massive, capturing huge atmospheres of hydrogen and helium. Then they migrated inward, over millions of years. They spiraled closer to their stars. They crossed the orbits of any rocky planets that might have been there. They either ejected those planets or consumed them. They reshaped their entire planetary systems, and they ended up in these scorching orbits where we find them today. This was a revolution in planetary science. We had to accept that planetary systems are dynamic, that planets migrate, that the arrangement we see today might be very different from how the system started, that our solar system, with Jupiter staying in the outer system, might be unusual. We now know that roughly 1% of Sun-like stars have hot Jupiters. That might not sound like much, but there are hundreds of billions of stars in our galaxy. 1% means billions of hot Jupiters exist, billions of gas giants locked in death grips with their stars, billions of worlds experiencing conditions we never imagined. And many of them are even more extreme than HD. 1, 8, 9, 7, 3, 3, b, or 51 Pegasi b. Let me tell you about the hottest planet ever discovered, Kelt 9b. This planet orbits a star about 670 light-years from Earth. The star itself is massive, roughly 2.5 times the mass of our Sun. It's what astronomers call an A-type star. These stars are hotter and brighter than our Sun. They burn through their fuel faster. They have shorter lifespans. But while they last, they blaze with incredible intensity. Kelt 9's surface temperature is around 18,000 degrees Fahrenheit, more than 3 times hotter than our Sun. The star emits tremendous amounts of ultraviolet radiation. Light so energetic it can break apart molecules. Light that would sterilize any nearby world. And Kelt 9b orbits this blazing star at only about 4 million miles. To put that in perspective, Mercury, the closest planet to our Sun, orbits at about 36 million miles. Kelt 9b is roughly 9 times closer to its star than Mercury is to ours. At that distance, The planet is receiving an absolutely staggering amount of radiation. The orbital period is 1.5 days, 36 hours. The planet races around its star at speeds exceeding 130 miles per second, faster than any planet in our solar system moves. The result of this proximity is a dayside temperature of around 7,800 degrees Fahrenheit. Let me put that in perspective. The surface of our Sun has a temperature of about 10,000 degrees Fahrenheit. Kelt 9b's dayside is nearly as hot as the surface of its own star, only about 2,000 degrees cooler than the star's photosphere. At these temperatures, matter behaves in ways we rarely see. Molecules can't hold together. Water would be torn apart into hydrogen and oxygen atoms. Carbon dioxide would split into carbon and oxygen. Even more complex molecules would be ripped to pieces by the intense heat. The atmosphere isn't made of gas in the traditional sense. It's made of individual atoms, a plasma of dissociated particles. Heavy metals, like iron and titanium, don't exist as solid or liquid. They exist as vapor. Atoms of iron float in the atmosphere like water vapor on Earth. Titanium is vaporized, scattered through the air. These aren't trace amounts. The atmosphere of Kelt 9b contains substantial quantities of vaporized metals. Scientists have detected iron, titanium, sodium, magnesium, chromium, all in atomic form, all floating in the superheated atmosphere. The planet is so hot that materials we think of as solid and permanent are treated like wisps of gas. Because Kelt 9b is tidally locked, the temperature difference between dayside and nightside is extreme. The dayside bakes at 7,800 degrees. The night side is cooler, maybe around 3,000 degrees Fahrenheit. Still hot enough to melt rock. Still hot enough to vaporize many materials. But thousands of degrees cooler than the dayside. This temperature gradient drives winds of unimaginable violence. The atmosphere on the dayside is heated to extreme temperatures. It expands, rises, creates massive low pressure. The night-side atmosphere is cooler and denser, high pressure. The pressure difference forces air to rush from night-side to dayside. Wind speeds on Kelt 9b potentially exceed thousands of miles per hour. Maybe 5,000, maybe more. We don't have precise measurements because the planet is so extreme, it pushes the limits of our instruments. But the physics suggests wind speeds that would make hurricanes on Earth seem like gentle breezes. These winds transport heat from the dayside to the night side. Without them, the temperature difference would be even more extreme. The dayside might be even hotter. The night side might be frozen solid. But the winds redistribute heat, creating a planet where the entire atmosphere is above the melting point of rock. But here's what makes Kelt 9b truly terrifying. It's being destroyed. The planet won't last. The intense radiation from its star is literally tearing Kelt 9b's atmosphere away. The process is called atmospheric escape. Ultraviolet light from the star hits atoms in the upper atmosphere. The light carries enough energy to ionize the atoms, stripping away electrons. This gives the atoms an electric charge. Charged particles can be accelerated by the star's magnetic field. They're flung away from the planet. And because Kelt 9b is so close to its star, and because the star is so active, this process is happening at an incredible rate, every second. Kelt 9b loses millions of tons of its atmosphere to space. Not a gradual leak, a torrent. The hydrogen is escaping fastest because it's the lightest element, but heavier elements are escaping too. Scientists have detected a massive cloud of escaping hydrogen around Kelt 9b. The cloud extends far beyond the planet itself. It's being blown away by the stellar wind, forming a long tail stretching behind the planet as it orbits. Like a comet, but made of the planet's own atmosphere, the metals are escaping too, though more slowly than hydrogen. Iron atoms, titanium atoms, all streaming away from the planet. Scientists estimate that Kelt 9b is losing mass at a rate that will completely strip away its atmosphere within a few million years. Maybe 10 million years. Maybe less. It's hard to calculate, precisely because the process depends on many factors. The strength of the stellar wind, the planet's magnetic field, if it has one, the composition of the atmosphere, but the conclusion is clear. Kelt 9b is dying. What happens when the atmosphere is gone? The planet might survive as a bare, rocky core. Gas giants likely have solid cores made of rock and ice. If Kelt 9b has such a core, it might remain after the atmosphere is stripped away. A scorched, lifeless ball of rock orbiting a blazing star. Or the planet might be completely consumed. As it loses mass, Kelt 9b's orbit might decay. It might spiral even closer to its star. Eventually, it could be torn apart entirely by tidal forces. The pieces would fall into the star. Kelt 9b would cease to exist. Either way, this planet has no future. We're watching it happen right now. In cosmic terms, Kelt 9b is in its final moments. A few million years from now, assuming anyone is around to look, this planet will be gone. All that will remain is a slightly more massive star, and maybe some debris. And this isn't unique to Kelt 9b. Many hot Jupiters are experiencing atmospheric escape. Many are losing their atmospheres to space. Some are dying slower than Kelt 9b. Some might be dying faster. But the process is the same. These planets migrated too close to their stars. Now they're paying the price. But let me tell you about WASP 12b, a planet being eaten alive in a different way. WASP 12b is located about 870 light-years from Earth, orbiting a yellow dwarf star similar to our Sun. The star is slightly more massive and hotter than our Sun, but it's recognizable. It's the kind of star we might expect to have planets like Earth. Instead, it has WASP 12b, a nightmare world locked in a death spiral. The planet is a gas giant, roughly 1.4 times the mass of Jupiter. But here's what's strange. Most gas giants are relatively compact. Jupiter's mass is packed into a sphere about 86,000 miles in diameter. Saturn is larger in radius, but less massive, more spread out because of its rapid rotation. WASP 12b is almost twice Jupiter's radius. It's puffed up to enormous size. A bloated giant, swollen far beyond what its mass should allow. Why? Because it's being cooked from the outside and torn apart by gravity. WASP 12b orbits its star at a distance of only about 2 million miles. That's roughly 50 times closer than Earth orbits the Sun. About 5% of Earth's orbital distance. At this range, the planet is receiving intense radiation. The orbital period is 1.09 days, roughly 26 hours. A year shorter than a single Earth day. The planet is moving at about 140 miles per second, racing around its star in this tight orbit. The dayside temperature reaches approximately 4,500 degrees Fahrenheit. Hot enough to melt rock. Hot enough to vaporize many materials. This heat is what's puffing up the atmosphere. The intense radiation from the star heats the outer layers of the planet. The gas expands. The planet swells. But the heat is only part of the story. The real terror of WASP-12b is tidal distortion. Tidal forces are what cause ocean tides on Earth. The moon's gravity pulls on the side of Earth, facing it more strongly than on the far side. This creates a bulge. The ocean rises on the near side and far side, creating high tides. On Earth, these tidal bulges are measured in feet or meters. The effect is gentle. But when a planet orbits very close to a star, the tidal forces become extreme. WASP-12b is so close to its star that the star's gravity pulls much harder on the near side than the far side. The gravitational gradient is enormous. The planet is being stretched, pulled into an egg shape, elongated along the axis, pointing toward the star. The planet's shape is no longer spherical. Computer models show WASP-12b distorted into a teardrop, the pointed end facing the star, the back end rounded. The planet is literally being pulled apart by gravity. And this distortion creates heat. As the planet orbits, the tidal bulge moves around. The planet flexes. The interior is constantly being compressed and relaxed. Compressed and relaxed. This flexing generates heat through friction. The same way, bending a piece of metal back and forth will make it hot. Inside WASP-12b, the constant flexing is heating the planet's core. This internal heat adds to the external heating from the star. Together, they puff up the atmosphere even more. The planet swells to nearly twice Jupiter's size, but it can't hold together forever. The combination of extreme heat and tidal distortion means the atmosphere of WASP-12b is escaping. Not just escaping, pouring off the planet. Scientists estimate that WASP-12b is losing about 6 billion tons of material every second. 6 billion tons. Every second. To put that in perspective, Earth's entire atmosphere weighs about 5 quintillion tons. WASP-12b is losing the equivalent of Earth's entire atmosphere every 26 million years or so. That sounds like a long time, but WASP-12b has been around for billions of years. It's lost enormous amounts of mass already, and the process is accelerating. As the planet loses mass, it shrinks slightly. As it shrinks, tidal forces become even more extreme relative to the planet's size. More mass is pulled away. The planet shrinks more. It's a runaway process. And the lost material doesn't just vanish into space. It forms a disk around the star. As atmosphere escapes from WASP-12b, the material is still moving. It still has orbital momentum, but it's no longer bound to the planet. Instead, it orbits the star. The escaping gas is drawn inward by the star's gravity. It spirals down, forming an accretion disk. Like the disks around young stars where planets form. Except this disk is made of the remains of a dying planet. The star is literally eating WASP-12b, consuming it bit by bit. Scientists have detected the chemical signatures of this process. They analyzed the star's spectrum, looking at the light it emits. They found unusually high levels of carbon. More carbon than a star like this should have. Where did the carbon come from? From WASP-12b. At the high temperatures in the planet's atmosphere, Chemical reactions create carbon-rich compounds. As this material escapes and falls onto the star, it changes the star's composition. The star is being polluted by the planet. Over time, the star is growing slightly more massive. WASP-12b is shrinking. The planet is literally being transferred to the star atom by atom. Scientists have calculated how long this can continue. WASP-12b has maybe 10 million years left, possibly less. After that, the planet's atmosphere will be completely gone. What remains might be a bare rocky core. Gas giants are thought to have solid cores made of rock and ice. These cores are where the planets began. Small, solid objects that grew large enough to capture massive atmospheres. If WASP-12b has such a core, it might survive the loss of the atmosphere. A small rocky planet would remain, orbiting close to the star, scorched, lifeless, but still there. Or the planet might be completely consumed. As WASP-12b loses mass, its orbit might change. It might spiral even closer to the star. At some point, it might cross the Roche limit. The distance at which tidal forces are strong enough to tear a planet apart completely. WASP-12b would be shredded. The pieces would fall into the star. Nothing would remain. Either way, 10 million years from now, WASP-12b as we see it today will be gone. The bloated gas giant, twice the size of Jupiter, will have disappeared. In cosmic terms, we're watching the final moments of this planet, billions of years of existence, ending in a few million years of destruction. And this fate isn't unique to WASP-12b. Many hot Jupiters orbiting very close to their stars are doomed. Those within a few million miles of their stars are all losing mass, all being slowly consumed. Some will last longer than WASP-12b. Some won't last as long, but eventually they'll be destroyed. Their migration brought them too close, and now they're paying the ultimate price. These hot Jupiters show us one type of extreme: planets being destroyed by proximity to their stars. But there are other worlds just as terrifying in completely different ways. Let me tell you about the lava planets. Worlds where the surface isn't just hot, it's molten. Liquid rock oceans covering entire hemispheres. K2141b is located about 200 light-years from Earth, orbiting a star similar to our Sun. The planet is roughly 1.5 times the size of Earth, about 8,600 miles in diameter, compared to Earth's nearly 8,000 miles. The estimated mass is about 5 times greater than Earth. That makes it a super-Earth, larger and more massive than our home world. Rocky, probably with an iron core and a silicate mantle like Earth. But any similarity to Earth ends there. K2141b orbits its star at a distance of only about 1,600,000 miles. To put that in perspective, Mercury orbits our Sun at about 36 million miles. K2141b is roughly 22 times closer to its star than Mercury is to ours. About 60 times closer than Earth orbits the Sun. At this distance, the orbital period is 0.38 days. That's 9.1 hours. A year on this planet is shorter than a workday on Earth. The planet completes its orbit in less time than it takes you to sleep, work, and come home. The planet is moving at about 200 miles per second just to stay in orbit, far faster than any planet in our solar system. At this distance, The amount of radiation the planet receives is staggering. K2141b receives approximately 3,000 times more energy from its star than Earth receives from the Sun, 3,000 times. On Earth, we receive about 1,360 watts per square meter of sunlight. On K2141b, the planet receives over 4 million watts per square meter. The result is a surface temperature estimated at around 4,500 degrees Fahrenheit on the day side. That's hot enough to melt any rock. Basalt, the volcanic rock that makes up most of Earth's ocean floor, melts at about 2,000 degrees Fahrenheit. Granite, the rock that makes up Earth's continents, melts at around 2,200 degrees Fahrenheit. Even refractory materials, substances with very high melting points, become liquid at 4,500 degrees. Tungsten, which has one of the highest melting points of any element, melts at 6,192 degrees Fahrenheit. On K2141b, we're approaching those temperatures. The entire day side of K2141b is likely covered in an ocean of lava, not pockets of lava, not volcanic lakes. An ocean. Liquid rock stretching from horizon to horizon, potentially hundreds of miles deep, glowing orange and red from its own heat. The surface would not be calm. Convection currents would churn the magma. Hot material from below would rise to the surface. It would cool slightly as it radiates heat to space. Then it would sink back down as denser material replaces it from below. The entire ocean would be in constant motion, churning, roiling, like water boiling violently in a pot. Waves would crash, not water waves, waves of molten rock, liquid stone rising and falling, splashing against any solid features that might exist. The violence would be extraordinary. And above this ocean, the atmosphere would be unlike anything on Earth. At temperatures hot enough to melt rock, rock doesn't just melt, it vaporizes. Silicates, the minerals that make up most rocks, can exist as gas at these temperatures. The atmosphere of K2141b is probably filled with vaporized rock. Silicon dioxide, the main component of sand and quartz, would exist as vapor. Magnesium oxide, iron oxide, calcium oxide, all floating in the air as gas. Clouds would form, but not clouds of water, clouds of condensed rock vapor. As this vapor rises and cools slightly, it might condense into tiny droplets. Liquid droplets of silicon and oxygen compounds. Liquid droplets of metals and minerals. Rain would fall, but not water rain. Rock rain. Droplets of liquid silicates falling back to the surface, adding to the ocean below. The atmosphere would be thick with this vaporized material, opaque. You couldn't see through it. Even hovering above the planet, you wouldn't be able to see the surface. The air itself would block your view, a dense haze of rock vapor and metal vapor glowing from the heat. And like most planets orbiting this close to their stars, K2141b is probably tidally locked. One side permanently faces the star. The other side faces away. The day side is this molten hellscape, an ocean of lava under an atmosphere of vaporized rock. The night side would be cooler. Not cool, but cooler. Maybe 2,000 degrees Fahrenheit. Still hot enough to glow dull red. Still far above the melting point of many materials. But cool enough that rock might solidify. Scientists think there might be a transition zone on the night side, a region where the temperature is just below the melting point of rock. Here, the lava ocean would end. The surface would be solid. But this wouldn't be a gradual transition. Not a beach where liquid slowly becomes solid, a sharp boundary. A shoreline where liquid rock meets solid rock. Waves of molten stone lapping against a coast of cooled basalt. Imagine standing on that shoreline, if you could somehow survive. On one side, a glowing ocean of liquid rock stretching to the horizon. On the other, a dark landscape of solid stone. The boundary between them would be in constant motion. The temperature fluctuates slightly based on atmospheric circulation. Sometimes, hot gas from the day side blows across the terminator. The temperature rises. The lava advances. It melts the solid rock at the edge. The ocean grows slightly larger. Then, the wind shifts. Cooler gas flows in from farther around the night side. The temperature drops. The lava at the edge solidifies. The ocean retreats slightly. This would happen continuously. The shoreline would never be stable, never be predictable. Always changing, always moving, always dangerous, and even the solid parts of the night side would be incredibly hostile. 2,000 degrees Fahrenheit. Hot enough to glow. Hot enough to instantly vaporize any organic material. Hot enough that standing on the surface would be like standing in a blast furnace. There's no place on K2141b that could be called safe. It's a world of extremes from one side to the other. But here's something that should make you think. Earth could have been a lava planet. Earth was a lava planet for a period in its history. About 4.5 billion years ago, shortly after our planet formed, something catastrophic happened. Earth collided with another planet, a Mars-sized object that astronomers have named Theia. We don't know exactly how the collision happened, whether Theia hit Earth directly or at an angle, whether it was a slow collision or a fast one. But we know it happened because of what it left behind: the Moon. The collision was unimaginably violent. Both planets were partially vaporized. Huge portions of their mantles were blown into space. The material formed a ring around Earth. Over time, this ring coalesced into the Moon. But the collision did something else too. It left Earth's entire surface molten. The energy released by the impact was enormous. Enough to melt the entire planet. For millions of years after the collision, Earth was covered in an ocean of magma, an ocean potentially hundreds of miles deep, covering the entire planet. The surface temperature was thousands of degrees. The atmosphere was filled with vaporized rock and metal, steam from vaporized water, carbon dioxide from vaporized carbonates, sulfur dioxide from vaporized sulfur compounds. The sky would have glowed from the heat. Everything was molten. Everything was chaos. It would have looked very similar to what we see on K2141b today, a world where the surface was liquid rock, where the atmosphere was filled with vapor that we normally think of as solid, where temperatures were so high that nothing could survive. Earth was a lava planet, but Earth was lucky. We were far enough from the sun that we could cool down. The surface began radiating heat into space. Slowly, over millions of years, the temperature dropped. The magma ocean began to solidify. First, a thin crust formed on the surface. Then it thickened. As it cooled, the crust cracked and broke. New magma welled up from below. But each time, a little more solid surface remained. Eventually, the entire surface solidified. A solid crust covered the planet. Water vapor in the atmosphere began to condense. It fell as rain, not just rain, a deluge that might have lasted thousands of years. The oceans formed. Lakes and rivers appeared. Earth became a water world. And eventually, life arose in those oceans. Simple, single-celled organisms at first. Then, more complex life. Eventually, life spread to land, plants, animals, and ultimately humans. All of this was possible because Earth cooled down, because we were far enough from the sun. But if Earth had formed closer to the sun, we would never have cooled down. The sun's heat would have kept the surface molten. Earth would have remained a lava planet forever. No solid crust, no oceans, no continents, no life, just liquid rock and vaporized minerals under a sun that never allows the surface to solidify. K2141b. And the other lava planets we're discovering aren't alien oddities. They're not strange exceptions to how planets should be. They're what Earth could have been with a slightly different orbit. They're planets that never got the chance to cool down, never got the chance to develop the stable conditions that allow life to arise. They're locked in the earliest, most violent phase of planetary evolution. And they'll stay there as long as they remain this close to their stars. Forever molten, forever hostile, forever lifeless. Now let me tell you about planets that shouldn't exist at all. Planets orbiting dead stars. PSR B1829-10 is a pulsar located about 9,800 light-years from Earth, deep in the constellation Sagittarius. Pulsars are among the strangest objects in the universe. They're the collapsed cores of massive stars that have gone supernova. Let me explain what that means. When a star much larger than our Sun runs out of fuel, something catastrophic happens. For most of its life, a star is in balance. Gravity pulls inward, trying to collapse the star. The pressure from nuclear fusion in the core pushes outward, resisting collapse. As long as the star is fusing hydrogen into helium, this balance holds. But eventually, the hydrogen runs out. The star begins fusing helium into heavier elements. Carbon, oxygen, neon, magnesium. Each stage of fusion requires higher temperatures. Each stage produces less energy. Eventually, for massive stars, the core begins fusing silicon into iron, and that's where the process stops. Iron is the most stable element. Fusing iron doesn't release energy. It consumes energy. So, when a massive star's core becomes iron, fusion stops. There's no outward pressure. Nothing to resist gravity. The core collapses. In less than a second, a core the size of Earth collapses to a sphere about 12 miles across. The density becomes unimaginable. Protons and electrons are crushed together, forming neutrons, a neutron star. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The entire mass of our Sun compressed into a sphere the size of a city. But the collapse does something else too. It releases an enormous amount of energy. Energy that blows away the outer layers of the star, a supernova. One of the most violent events in the universe. For a few weeks, a supernova can outshine an entire galaxy. Billions of stars, dimmed by the light of one exploding star. The outer layers of the star are blown away at thousands of miles per second, 10,000 miles per second, 20,000 miles per second. Moving so fast that they create shockwaves in the interstellar medium. The explosion releases more energy in a few seconds than our Sun will release in its entire 10 billion-year lifetime. Anything close to a supernova is destroyed. Planets, if they existed, would be vaporized. The intense radiation would strip away their atmospheres. The shock wave would tear them apart. Nothing should survive. And yet, PSRB 1829-10 has a planet. In 1991, astronomers Alexander Wolszczan and Dale Frail were studying this pulsar. Pulsars spin rapidly and emit beams of radiation from their magnetic poles. As the pulsar rotates, these beams sweep across space like a lighthouse. If Earth happens to be in the path of one beam, we detect regular pulses of radiation. PSRB 1829-10 spins once every 0.303 seconds. That's roughly 317 rotations per minute. 317 times per minute, the pulsar's radiation beam sweeps past Earth. We detect it as a pulse. The pulses are incredibly regular. More regular than any clock we've built. But Wolszczan and Frail noticed something strange. The pulses weren't perfectly regular. They showed tiny variations, periodic shifts in timing. The pulses were arriving slightly earlier than expected, then slightly later, in a repeating pattern. There was only one explanation. A planet was orbiting the pulsar. As the planet orbited, its gravity caused the pulsar to wobble slightly. This wobble changed the distance between the pulsar and Earth by a tiny amount. When the pulsar was slightly closer, the pulses arrived earlier. When it was slightly farther, the pulses arrived later. By measuring these timing variations, astronomers could detect the planet. They could calculate its mass, its orbital period, its distance from the pulsar, all from tiny shifts in the arrival time of pulses. PSR B 1829-10b is about 4 times the mass of Earth. It orbits its pulsar at roughly 350 million miles, about the same distance as the asteroid belt in our solar system. It completes one orbit every 67 days. But this planet shouldn't exist. When the massive star that became this pulsar went supernova, the explosion should have destroyed any planets orbiting it. The blast would have torn them apart. The radiation would have vaporized them. The shock wave would have blown them into interstellar space. Nothing should have survived. So, either this planet somehow survived the supernova, which seems impossible, or it formed after the supernova. Scientists now think the latter is true. After the supernova, debris from the explosion formed a disk around the neutron star, material that didn't escape, material that fell back and began orbiting. Over time, this material coalesced. Particles stuck together. Larger objects formed. Eventually, planets emerged from the debris. These pulsar planets are sometimes called zombie planets. Because they rose from the death of a star, they formed in the aftermath of destruction. But what makes PSR B 1829-10b terrifying isn't how it formed. It's the environment it exists in. The radiation. Pulsars emit intense beams of electromagnetic radiation from their magnetic poles. Not just radio waves, X-rays, gamma rays. Among the most energetic forms of radiation in the universe. The magnetic field of a pulsar is trillions of times stronger than Earth's magnetic field. This field accelerates charged particles to nearly the speed of light. These particles emit radiation as they spiral around the magnetic field lines. The result is beams of incredibly intense incredibly energetic radiation. If you were standing on the surface of PSRB 1829-10b, you would be bathed in this radiation every time the pulsar's beam swept across the planet. And it sweeps across 317 times every minute. The radiation dose would be millions of times higher than what you experience on Earth. Maybe billions of times higher. It would kill any living thing in seconds. It would break apart DNA. It would destroy proteins. It would shred any complex molecules. Even simple molecules would be torn apart. Water would be split into hydrogen and oxygen. Carbon dioxide would be broken into carbon and oxygen atoms. The surface would be bombarded continuously. Sterilized completely. Nothing could survive. And the radiation would strip away any atmosphere the planet might have. High-energy photons hitting atmospheric molecules would give them enough energy to escape. Over time, the atmosphere would be blown away, leaving a bare, lifeless rock. And there's no escape. No hiding from this radiation. It's not occasional. It's constant. 317 times every minute, every hour, every day. For billions of years. PSR B 1829-10b is a dead world orbiting a dead star, a corpse of a planet circling the corpse of a star, exposed to radiation that would destroy anything we could imagine. It's a monument to the universe's capacity for creating environments utterly incompatible with life. And it's not alone. Since the discovery of PSRB 1829-10b, astronomers have found other pulsar planets. Not many, because they're hard to detect, but enough to know that they're not unique. Planets can form in the aftermath of supernovae. Life can emerge from death, at least planetary life, but not biological life. These worlds are sterile, forever. But perhaps the most unsettling planets drift alone through space. The rogue planets, worlds that don't orbit any star at all. They wander the galaxy in darkness, alone. CFBDSIR 2140-723 is one of these orphaned worlds. It's located about 100 light-years from Earth. Or at least, it was 100 light-years from Earth when we detected it. It's moving through space, and we don't know exactly where it's going. Scientists estimate its mass at somewhere between 4 and 7 times the mass of Jupiter. A gas giant, but unbound to any star. It's probably between 50 million and 120 million years old, relatively young in cosmic terms, still cooling down from its formation. The estimated surface temperature is around 750 degrees Fahrenheit. That might sound hot, but remember, this heat isn't coming from any external source. There's no star heating this planet. The heat is left over from the planet's formation. When gas giants form, gravitational energy is converted to heat. The planet starts out hot. Over time, it radiates this heat into space and cools down. CFBDSIR 2140-723 is still in this cooling phase. But eventually, in a few billion years, it will be cold, maybe just a few degrees above absolute zero. The coldest temperature theoretically possible. Imagine what CFBDSIR 2140-723 looks like. There's no sun, no star anywhere nearby. The closest stars would be light years away. Distant points of light, too far away to provide any heat, too far away to even appear as disks. just points. The sky would be black, completely black except for stars. More stars than you could count. The Milky Way would stretch across the sky, a band of light made of billions of distant suns, but none of them would be close. None of them would be this planet's star, because this planet has no star. The planet itself might glow faintly in the infrared from its own internal heat, but to human eyes, it would be dark, no light reflecting off clouds. No illuminated atmosphere, just darkness. If this planet has an atmosphere, and it probably does, it would be strange. With no sunlight to drive weather patterns, there would be no traditional meteorology. No day or night cycles. No seasons. No variation in temperature based on position. Just slow, gradual cooling over billions of years. Any atmospheric movement would be driven by the planet's rotation and internal heat. If the planet is rotating, and it probably is, the rotation would create winds. The Coriolis effect would organize these winds into bands, similar to the bands we see on Jupiter. But without sunlight, without external heating, these winds would be different, driven entirely by heat escaping from the interior. If there are clouds in the atmosphere, they would be made of exotic materials. Not water ice, like clouds on Earth. Maybe ammonia ice. Maybe methane ice. Maybe silicate clouds, if the planet is still hot enough. As the planet cools over billions of years, these clouds would change. Ammonia would condense and fall out, raining onto whatever lies below. Methane would freeze and fall. Eventually, even hydrogen and helium might liquefy at the surface if the planet gets cold enough. The atmosphere would become thinner as gases condense. Or it might become thicker if the planet has enough mass to hold onto even the lightest elements. We don't know. We've never studied a rogue planet up close. All we have are theoretical models. If CFBDSIR 2140-723 has a surface, which it might not as a gas giant, that surface would be completely dark, no sunlight ever. No day, no night, just eternal darkness. The only light would be from the stars. Starlight so faint it would barely illuminate anything. You wouldn't be able to see your hand in front of your face. The temperature on the surface, assuming there is one, would eventually drop to near absolute zero. Nothing would move. Nothing would change. No geological activity, because there's no tidal heating. No volcanoes, because there's no star to create tidal forces. Just cold, dark, silent, forever. No life as we understand it could exist here. Life needs energy. On Earth, almost all life gets its energy from the sun. Plants photosynthesize. Animals eat plants or eat other animals that ate plants. The whole ecosystem is powered by sunlight. Even life that doesn't depend directly on photosynthesis, like creatures living near deep-sea hydrothermal vents, exists in an ecosystem that's ultimately connected to the sun. The oxygen they breathe was produced by photosynthesis. The organic matter that falls from above was created by photosynthesis. On a rogue planet, there's no sunlight, no photosynthesis, no oxygen production, no energy input except the slowly fading heat from the planet's formation. Maybe, theoretically, life could exist using chemical energy, reactions between minerals and whatever atmosphere exists. But it would be incredibly limited, low energy, slow, probably just microbes, if anything, and even that seems unlikely. A rogue planet drifting through interstellar space is probably sterile, lifeless, dead, and it will remain that way forever. Rogue planets form in one of two ways. Some form around a star and then get ejected. In a young planetary system with multiple planets, gravitational interactions can be chaotic. Planets can scatter each other. One planet might be thrown into a highly elliptical orbit. Another might be ejected completely. Thrown out of the system with enough velocity to escape the star's gravity, it becomes a rogue, wandering the galaxy alone. Other rogue planets might form independently, not around a star, but in interstellar clouds of gas. If a cloud is dense enough, parts of it can collapse under their own gravity. Usually, this forms a star, but sometimes the collapsing region isn't quite massive enough. It forms a planet instead, a planet that never had a star, born alone. Either way, these planets end up drifting through space. No orbit, no sun, just motion through the galaxy. They'll continue moving for billions of years. Eventually, maybe, one might be captured by a star. If a rogue planet passes close enough to a star, gravity might capture it into orbit. It would become a planet again, but this is rare. Most rogue planets will drift forever. We've detected a handful of rogue planets. Not many, because they're incredibly hard to find. They don't emit their own light, at least not much. They're not orbiting a star that we can use to detect them. We can't use the transit method. We can't use radial velocity. We can only find them through gravitational microlensing. When a massive object passes between us and a background star, its gravity bends the light from that star. The star appears to brighten temporarily. By analyzing the brightening, we can detect the object even if we can't see it directly. This technique has revealed a few rogue planets, but it's biased toward massive planets. Small, rocky planets would be almost impossible to detect this way. We've also detected a few young rogue planets through their infrared glow, planets that are still hot from formation, like CFBDSIR 2140-723. But older, colder rogue planets would be invisible to us. And here's the disturbing part. Some estimates suggest there could be billions of rogue planets in our galaxy alone, maybe even more than planets orbiting stars. For every star with planets, there might be dozens of rogue planets drifting through the darkness. They're just invisible to us. We can't see them. We can't detect them. They're out there, right now, passing through interstellar space. Maybe some are passing through our region of the galaxy. Maybe one has passed relatively close to our solar system, within a few light years. We would never know, unless it happened to pass in front of a background star at exactly the right time. The galaxy might be filled with these dark worlds, outnumbering the planets we can see. A hidden population of orphaned worlds, wandering forever in the void between the stars. It's a disturbing thought. The universe might be full of planets, but most might be frozen, lifeless rogue worlds, drifting forever through empty space, never to be discovered, never to be studied, just existing in darkness, alone. Now let me tell you about planets that are common but completely alien to our experience. The super-Earths. These planets dominate the exoplanet catalog. They're the most common type of planet we've discovered. And yet, we have nothing like them in our own solar system. In our solar system, there's a clear gap in planetary masses. We have rocky planets that are relatively small. Mercury is the smallest, at about 0.055 Earth masses, just over 5% of Earth's mass. Mars is larger, at about 0.1 Earth masses, roughly 11% of Earth's mass. Venus is similar to Earth, at 0.82 Earth masses, 82% of Earth's mass. And Earth is, of course, 1 Earth mass. These are our rocky planets, small, dense, made primarily of rock and metal. Then we have the gas giants. Uranus and Neptune are the smallest at roughly 14.5 and 17 Earth masses respectively, still massive compared to Earth, about 15 to 17 times more massive. Saturn is 95 Earth masses. Jupiter is 318 Earth masses. These are our gas giants. Massive planets made primarily of hydrogen and helium with possible rocky cores. There's a clear gap from 1 Earth mass for Earth itself. We jump to roughly 15 Earth masses for Uranus. Nothing in between. No planets with masses of 2, 3, 5, or 10 Earth masses. The gap is empty in our solar system. We thought this might be normal, that planetary systems naturally sorted into small rocky planets and large gas giants. But when we started finding planets around other stars, we discovered the gap is actually filled. Most stars have planets in this mass range, planets with masses between 1 and 10 Earth masses. We call them super-Earths, though the name is somewhat misleading. They're not just larger versions of Earth. They're a genuinely different category of planet, and we don't fully understand what they are, because we can measure a planet's mass using radial velocity. The wobble the planet induces in its star tells us the mass, and we can measure a planet's radius using the transit method. When a planet passes in front of its star, it blocks some light. The amount of light blocked tells us the planet's size. But composition requires more detailed observations. Is a 5 Earth mass planet rocky, like Earth? Or does it have a thick atmosphere of hydrogen and helium, like Neptune? Or is it something in between? The answer depends on where the planet formed, how much gas it captured, whether it migrated inward or stayed where it formed. We're still figuring this out for most super-Earths. Some are probably rocky, large versions of Earth with thick crusts and deep mantles. Others are probably more like small Neptunes. Rocky cores surrounded by thick atmospheres of hydrogen and helium, and some might be completely different. Water worlds with deep oceans. Carbon planets with diamond mantles. Planets with compositions we haven't even imagined. The diversity is enormous, and many of these super-Earths orbit close to their stars, experiencing extreme conditions. Gliese 486b is one of these. It orbits a red dwarf star about 26 light-years from Earth. Red dwarfs are the most common type of star in the galaxy. They're small, cool, and they burn their fuel very slowly. A red dwarf can last for trillions of years, far longer than our sun's expected 10 billion-year lifespan. But red dwarfs have problems. They're active, producing frequent flares, and they're cool, so planets need to orbit very close to be warm enough for liquid water. Gliese 486b orbits very close. The planet is classified as a super-Earth with a mass roughly 3 times that of Earth, about 3.1 Earth masses. The radius is about 1.3 times larger than Earth's. From these measurements, Scientists calculated the density, and the density suggests Gliese 486b is probably rocky. Similar composition to Earth. Iron core, silicate mantle, possibly a thin crust. But that's where the similarity ends. Gliese 486b orbits its star in only 1.47 days. Roughly 35 hours, a year shorter than 2 Earth days. The planet is tidally locked. One side always faces the star, the other side always faces away. And the temperature on the day side is estimated at around 850 degrees Fahrenheit, hot enough to melt lead, hot enough to vaporize water. What makes Gliese 486b particularly interesting is that it probably has an atmosphere. Scientists have detected evidence of atmospheric gases using spectroscopy, possibly water vapor, possibly other compounds. But any water on Gliese 486b would exist in a state we rarely encounter on Earth. At 850 degrees Fahrenheit, and at the pressures likely on this planet, water doesn't behave normally. On Earth, water exists in 3 familiar states: ice below 32 degrees Fahrenheit, liquid water between 32 and 212 degrees Fahrenheit, steam above 212 degrees Fahrenheit. But these phase transitions depend on pressure. At higher pressures, water can remain liquid. At higher temperatures, at lower pressures, water boils at lower temperatures. On mountaintops where air pressure is lower, water boils at less than 212 degrees. In a pressure cooker, where pressure is higher, water can be heated above 212 degrees without boiling. But there's a special point called the critical point. For water, the critical point occurs at around 705 degrees Fahrenheit and a pressure of about 218 atmospheres. Above this temperature and pressure, the distinction between liquid and gas breaks down. Water becomes what's called a supercritical fluid. It has properties of both liquid and gas. It can flow like a liquid, filling containers, but it also expands to fill available space like a gas. The density is somewhere between liquid and gas. On Gliese 486b, at 850 degrees and likely high atmospheric pressure, water would be supercritical, not liquid, not gas, something in between. Supercritical water is strange stuff. It's an extremely good solvent, better than liquid water. It can dissolve materials that normal water can't touch. Salts, minerals, even some organic compounds that are normally insoluble. It's also very reactive. At supercritical conditions, water can participate in chemical reactions that don't happen at normal temperatures and pressures. If you were surrounded by supercritical water on Gliese 486b, it wouldn't be like swimming. It wouldn't be like breathing. It would be like being immersed in a hot, dense, chemically aggressive fluid. The supercritical water would penetrate anything. It would dissolve organic matter. It would react with materials. There would be no protective suit that could withstand it. No material that wouldn't eventually be corroded or dissolved. And this might be common on super-Earths. Many super-Earths orbit close to their stars where temperatures are high. If they have water, it might exist in supercritical form. Planets with entire atmospheres of supercritical water, or supercritical carbon dioxide, or other compounds in exotic states. These aren't worlds we can relate to. They're fundamentally alien in ways that gas giants aren't. At least with gas giants, we have Jupiter and Saturn as examples. With super-Earths, we have nothing similar in our solar system. We're discovering a category of planet that's common in the universe but completely absent from our own experience. Another super-Earth, 55 Cancri E, might be even stranger. This planet is about 41 light-years from Earth, roughly twice Earth's diameter, and about 8 times Earth's mass. 55 Cancri E orbits very close to its star, completing one orbit every 18 hours. The surface temperature is estimated at around 3,600 degrees Fahrenheit. Based on the planet's mass and size, scientists calculated its density. The numbers suggested something shocking. 55 Cancri E might have a thick layer of diamond under its surface. Carbon can exist in different forms depending on temperature and pressure. At Earth's surface, carbon forms graphite. Under high pressure and high temperature, carbon forms diamond. If a planet forms in a region rich in carbon compounds, and if conditions are right, that carbon could crystallize into diamond. Scientists estimate that up to 1/3 of 55 Cancri E's mass could be carbon in the form of diamond. If true, this planet might have a layer of diamond hundreds of miles thick beneath its surface. We should be cautious. This is based on models and density calculations. More recent observations suggested the planet might have more oxygen and less carbon. It might not be a diamond planet, after all. But even if it's not, the fact we're discussing the possibility tells you something. Super-Earths can have compositions wildly different from Earth. They're not just scaled-up versions of our planet. They're genuinely alien worlds, with chemistry and geology completely unlike anything we're familiar with. Now, let me tell you about planets in the habitable zone that are anything but habitable. TRAPPIST. 1 is a red dwarf star, located about 40 light-years from Earth. It's small, roughly the size of Jupiter, and cool. In 2017, astronomers discovered TRAPPIST. 1 hosts 7 Earth-sized planets. All 7 orbit very close to the star. The entire system would fit inside the orbit of Mercury. 3 of these planets, including TRAPPIST-1e, orbit within the habitable zone, the region where liquid water could theoretically exist. TRAPPIST-1e completes one orbit every 6.1 days. The planet receives about the same amount of light and heat as Earth receives from the Sun. Scientists estimate the surface temperature could be around 30 degrees Fahrenheit. On paper, TRAPPIST-1e sounds like it could be habitable, Earth-sized, right temperature, possibly rocky. But there's a problem. Like almost all planets orbiting very close to their stars, TRAPPIST-1e is probably tidally locked. One side always faces the star. The other side always faces away. The day side would be in permanent daylight. The sun would never set, never move across the sky. It would hang in one spot, forever, unchanging. The night side would be in permanent darkness. No sun, no light, except possibly the faint glow of stars. The temperature difference between the two hemispheres would be extreme. The day side might be warm enough for liquid water. The night side would be frozen solid. Any atmosphere would flow from hot side to cold side, creating permanent winds. The only potentially habitable region would be the terminator, the boundary between day and night. A narrow band circling the planet where the sun sits permanently on the horizon. Here, temperatures might be moderate enough for liquid water, a thin strip where conditions might be stable enough for life. But even this region would be hostile. Red dwarf stars are active. They produce frequent flares, sudden bursts of radiation thousands of times more powerful than anything our sun produces. TRAPPIST-1 is known to flare. These flares would bathe the planet in X-rays and ultraviolet light. Any life on the surface would need to hide underground during flares or develop extreme radiation resistance. The flares aren't occasional. They happen regularly, maybe multiple times per day. TRAPPIST-1e might be in the habitable zone by temperature, but it's far from comfortable. Permanent day on one side, permanent night on the other. Constant winds, regular radiation storms. When a planet is tidally locked, temperature extremes create permanent atmospheric circulation. On the day side, air heats up and rises. On the night side, air cools and sinks. This creates constant wind from night side to day side at low altitudes, from day side to night side at high altitudes. A permanent circulation that never stops. On some tidally locked planets, high in the atmosphere, winds race from day side to night side at incredible speeds. On some hot Jupiters, these jets reach speeds over 5,000 miles per hour. These winds transport heat from day side to night side, but they also create extreme wind shear. The difference in wind speed between the jet and lower atmosphere can be thousands of miles per hour over just a few miles of altitude. And there are planets with even more extreme orbital configurations. HD 80606b is located about 190 light-years from Earth. It's a gas giant, roughly 4 times the mass of Jupiter. But its orbit is unlike anything in our solar system. HD 80606b has an orbital eccentricity of 0.933. An eccentricity of 0 is a perfect circle. Earth's orbit has an eccentricity of about 0.017, nearly circular. HD 80606b's orbit is almost a straight line. At its closest approach to the star, the planet is about 2.8 million miles away, closer than Mercury gets to our Sun. At its farthest point, the planet is about 79 million miles away, about the distance of Venus from our Sun. The planet swings from scorching heat to relative cold and back every 111 days. When HD 80606b is at closest approach, it's blasted with intense radiation. The dayside temperature might reach several thousand degrees Fahrenheit. Then, the planet swings outward. Over the next 55 days, it moves farther from the star. Temperature drops. Atmosphere that was boiling might freeze. Then, the planet swings back inward. Temperature rises again. Frozen atmosphere thaws, evaporates, becomes superheated. This cycle repeats every 111 days. The planet never reaches equilibrium. It's constantly being heated and cooled. Tidal forces during close approach would be enormous. As the planet swoops close, the star's gravity pulls harder on the near side than the far side. The planet stretches, deforms. Then, as it swings away, tidal forces relax. The planet flexes back. This constant flexing generates immense heat inside the planet. Now let me tell you why all of this matters. Why these extreme planets tell us something important about our place in the universe. For most of human history, we only knew planets in our solar system. 8 worlds orbiting our sun in what seemed like an orderly arrangement. We thought this was normal. We thought all planetary systems would follow the same pattern. Rocky planets close, gas giants far, stable, predictable orbits. We had good reasons to think this. The arrangement made physical sense based on how planets form. Close to a star, only heavy elements can condense. Iron, silicates, materials with high melting points. These build rocky planets. Farther out, temperatures drop. Water can freeze into ice. Even farther, methane and ammonia can freeze. These ices, combined with rock, build larger cores massive enough to capture hydrogen and helium from the surrounding disk, gas giants. This is a logical, predictable process, and it matched what we observed in our solar system, so we assumed it was universal. We were wrong. The universe is far more creative and far more chaotic than we imagined. Most planetary systems don't look like ours. Most have experienced violent upheavals that reshaped their architecture. Planetary migration is common, maybe even the norm. When a planet forms in a disk of gas and dust, that disk doesn't just sit there passively. It interacts with the planet. The planet's gravity creates waves in the disk. These waves carry angular momentum. The planet either gains or loses orbital energy, depending on the details. For many planets, the result is inward migration. The planet spirals toward the star. This can happen fast. A Jupiter-sized planet can migrate from the outer solar system to the inner solar system in less than 1 million years. That's incredibly fast in geological terms. And as the planet migrates inward, it reshapes the entire system. If there are rocky planets in the way, they're either ejected or consumed, thrown out of the system entirely, or absorbed into the migrating giant. The final arrangement can be completely different from how the system started. Hot Jupiters are evidence of this process. They formed far from their stars, then migrated inward. Now, they orbit closer than Mercury. But migration isn't the only chaos. There's also planetary scattering. In a system with multiple large planets, gravitational interactions can become unstable. Computer simulations show this happening frequently. 2 planets on initially stable orbits can perturb each other. Their orbits become eccentric, elongated. They cross each other's paths. Eventually, they have a close encounter. One planet is thrown into a highly elliptical orbit. The other might be ejected completely, becoming a rogue planet, or both might be thrown out. Or they might collide, merging into a single, larger planet, or shattering into fragments. This is violent and unpredictable. Many planets don't survive. The ones we see today are the survivors, the lucky ones that made it through the chaos. And they're not necessarily in the orbits where they formed. They might have migrated. They might have been scattered. They might have had close encounters with other planets that changed their orbits. The final configuration reflects billions of years of dynamic evolution, not the initial conditions, and the type of star matters enormously. Our Sun is a G-type star, yellow, medium-sized, relatively stable. But G-type stars are not the most common. Red dwarf stars, M-type stars, make up about 70% of all stars in the galaxy. They're small, cool, and incredibly long-lived, but they're also active. Young red dwarfs produce frequent, powerful flares, bursts of radiation, thousands of times more energetic than anything our Sun produces. These flares emit X-rays and ultraviolet light, radiation that can strip away planetary atmospheres. Over billions of years, a planet orbiting a red dwarf might lose its entire atmosphere to these flares. And, because red dwarfs are cool, any planet in the habitable zone has to orbit very close, within a few million miles. This puts it directly in the path of the flares. There's no safe distance. Orbit far enough to avoid the worst flares, and you're too cold for liquid water. Orbit close enough to be warm, and you're being blasted with radiation regularly. Most stars are red dwarfs. Most potentially habitable planets orbit red dwarfs, and most of those planets are probably hostile to life because of the radiation. Then there are massive stars, O and B type stars. These are rare, making up less than 1% of all stars, but they're incredibly hot and bright. They emit enormous amounts of ultraviolet radiation. Any planet close enough to be warm would be scorched. The radiation would prevent complex organic molecules from forming. Life, as we know it, couldn't arise. And massive stars don't last long. An O-type star might only live a few million years. That's not enough time for life to evolve. Life on Earth took billions of years to develop. Single-celled organisms first, then multicellular life, then complex animals, then intelligence. A planet orbiting a massive star wouldn't have time. The star would die before life got started. So, most stars aren't suitable for life. Red dwarfs are too active. Massive stars are too short-lived. That leaves stars like our Sun. G-type stars, K-type stars, maybe F-type stars. These make up maybe 15 to 20% of all stars. And even among these, most have planetary systems that experienced chaos, migration, scattering, collisions. Most don't have stable, habitable zones where a planet could orbit peacefully for billions of years. This is what the extreme exoplanets teach us. They show us what's normal in the universe: chaos, extremity, hostility, and they make Earth's calm, stable existence seem extraordinary, because it is extraordinary. Let me tell you what had to happen for Earth to be habitable. First, we needed the right star. Not too massive, not too small, not too active. A G-type star like our Sun. That narrows it down to maybe 10% of all stars. Second, we needed to form at the right distance. Close enough to be warm, but not so close that we'd be a lava planet. Far enough to avoid being scorched, but not so far that we'd be frozen. In the habitable zone. That's a narrow range. For our Sun, the habitable zone extends from about 90 million miles to about 140 million miles. Earth formed at 93 million miles, solidly in the middle. Third, we needed a nearly circular orbit. If Earth's orbit were highly eccentric, we'd swing from too hot to too cold. Life couldn't adapt to such rapid changes. Our eccentricity is only 0.017, nearly circular. Fourth, we needed to avoid migration. If Earth had migrated inward, we'd be too hot. If we'd migrated outward, we'd be too cold. We stayed where we formed. Fifth, we needed the right mass. Too small, and we couldn't hold on to an atmosphere. Too large, and we'd capture a thick hydrogen atmosphere like Neptune. Earth is just right. Massive enough to hold nitrogen and oxygen. Small enough that we don't have a crushing hydrogen atmosphere. Sixth, we needed water, but not too much. Earth is about 0.02% water by mass. Enough for oceans. Not so much that we're a water world with no land. Seventh, we needed the right neighbor planets. Jupiter formed in the outer solar system. Its gravity shields us from many comets and asteroids. But Jupiter didn't migrate inward. If it had, it would have disrupted Earth's orbit, or thrown Earth out of the system entirely. We were lucky. Eighth, we needed a large moon. The moon stabilizes Earth's axial tilt. Without it, our tilt would vary chaotically. Climate would be unstable. Seasons would be extreme. The moon formed from the Theia impact. That impact could have destroyed Earth. Instead, it gave us the moon. Ninth, we needed plate tectonics. The carbon cycle regulates our climate over millions of years. Without it, carbon dioxide might build up, creating a runaway greenhouse like Venus. Or carbon might be locked away, freezing the planet. Plate tectonics keeps the balance. 10th, we needed a magnetic field, generated by our liquid iron core. This protects our atmosphere from solar wind. Mars lost its magnetic field. Its atmosphere was stripped away. Earth kept its magnetic field. Our atmosphere remained. 11th, we needed time, billions of years of stable conditions. No nearby supernovae, no gamma-ray bursts, no asteroid impacts large enough to sterilize the planet. Earth has had 4 billion years of relative stability. That's rare. 12th, we needed luck. Random chance played a role. The right materials in the right place. The right timing for planetary formation. The right gravitational interactions. Everything had to line up, and it did. All 12 of these factors aligned. Maybe more factors we don't even know about yet. The result is Earth, a calm, stable, habitable planet. But most planetary systems don't have all these factors. Most experienced chaos. Most have planets in extreme orbits. Most are hostile. When we look at exoplanets, we're seeing what's normal. And normal is extreme. Earth is the exception. The rare, calm planet in a galaxy full of chaos. This doesn't mean life is impossible elsewhere. It means life is probably rare. The universe is huge. Hundreds of billions of galaxies, each with hundreds of billions of stars. Even if habitable planets are 1 in a million, that's still millions of habitable worlds in our galaxy alone. But they're spread out. The nearest might be hundreds of light years away, too far to visit with any technology we can imagine. We might be effectively alone, even if we're not literally alone. Our telescopes are getting better, much better. The James Webb Space Telescope launched in December 2021. It's the most powerful space telescope ever built. Webb's primary mirror is 21 feet across, made of 18 hexagonal segments coated in gold. The gold coating reflects infrared light efficiently, and infrared is what Webb is designed to detect. Infrared light can pass through dust clouds that block visible light. It can reveal objects that are too cool to glow visibly, and it can detect the heat signatures of exoplanet atmospheres. Webb orbits the Sun about 1 million miles from Earth, at a point called L2, the second Lagrange point. Here, Earth and the Sun's gravity balance. Webb can stay in a stable orbit with minimal fuel. The telescope is already making discoveries. It's detected water vapor in exoplanet atmospheres, finding evidence of sulfur dioxide and carbon dioxide, molecules that tell us about atmospheric chemistry, about what's happening on these distant worlds. Over the next decade, Webb will study hundreds of exoplanets. It will analyze their atmospheres in detail, looking for biosignatures, chemical combinations that might indicate life, oxygen and methane together, for example. On Earth, these gases coexist because life produces them. Oxygen from photosynthesis, methane from bacteria and other organisms. Without life constantly replenishing them, they'd react and disappear. If we find them together on an exoplanet, it might mean life. Webb will also find new types of extreme planets. Planets we haven't imagined yet. Worlds with atmospheric chemistry we've never seen. Temperatures in ranges we haven't explored. The universe is creative. There are almost certainly planets out there, stranger than anything we've found so far. And Webb will find them. The Nancy Grace Roman Space Telescope will launch in the mid-2020s. It's designed differently than Webb. Roman has a wide field of view. It can survey large areas of sky quickly. It will find thousands of new exoplanets using a technique called gravitational microlensing. When a star passes in front of a background star, its gravity bends the light. The background star appears to brighten temporarily. If the foreground star has a planet, the planet's gravity creates an additional brightening, a signature we can detect. This technique can find planets at large distances from their stars, cold planets in Jupiter like orbits, even rogue planets drifting through interstellar space. Roman will reveal a population of planets we've barely detected so far. The cold outer worlds, the distant ice giants, the rogue planets. It will show us the full diversity of planetary systems. Not just the hot planets close to their stars that are easy to detect, but everything. The European Space Agency's Plato mission will launch around 2026. Plato stands for planetary transits and oscillations of stars. It will search for Earth-sized planets in the habitable zones of Sun-like stars, using the transit method, watching for the tiny dip in starlight when a planet passes in front of its star. Plato will monitor millions of stars, looking for the rarest, most valuable planets, worlds that might actually be habitable. Not extreme, not hostile, just Earth-like. We don't know if such planets are common or rare. We've found a few candidates, but we need better data. Plato will provide that data. And ground-based telescopes are improving too. The extremely large telescope is being built in Chile's Atacama Desert. It will have a mirror 39 meters across. That's about 128 feet. 4 times larger than any optical telescope currently operating. With such a large mirror, the ELT will be able to directly image some exoplanets, seeing them as actual points of light separate from their stars. This is incredibly difficult. A planet next to its star is like a firefly next to a searchlight. The star is millions or billions of times brighter. Separating the planet's light from the star's glare requires extraordinary precision. But it's possible. Using coronagraphs to block the star's light, using adaptive optics to correct for atmospheric distortion, using sophisticated data processing to tease out the faint signal of the planet. Direct imaging will allow us to study exoplanets in ways we can't with other methods. We'll measure their temperatures directly, watch for seasonal changes, detect weather patterns, maybe even see continents and oceans if the planet is large and close enough. All of this is coming in the next 10 to 20 years. We're going to discover thousands more planets. We're going to characterize them in detail. We're going to find worlds even stranger than anything we've seen so far. And yes, we're probably going to find more nightmare planets, more worlds with glass rain, more planets being torn apart by their stars, more lava planets with molten surfaces, more rogue planets drifting through the void. But we might also find something else. We might find a planet that looks like Earth, a rocky world, the right size, the right temperature, with liquid water on its surface, an atmosphere with oxygen and methane, chemical signatures suggesting the presence of life. We might find it in the next decade, or the decade after that. It's possible. We have the technology. We're building the telescopes. We're developing the techniques to detect biosignatures in distant atmospheres. If there's a living world within a few hundred light years of Earth, we'll find it. And that discovery would change everything. It would tell us we're not alone, that life can arise elsewhere, given the right conditions, that the universe, hostile as it is, can still produce worlds where life thrives. It would be the most important scientific discovery in human history. Proof that life exists beyond Earth, that we're part of something larger. But even if we don't find life, the search is valuable. Every exoplanet we discover teaches us something about planetary formation, about atmospheric dynamics, about geology on alien worlds, about the diversity of conditions that can exist, about what makes Earth special. The extreme planets, terrifying as they are part of this story. They show us the boundaries of what's possible. They reveal processes we never imagined. They force us to expand our understanding of what a planet can be, how it can behave, what conditions it can endure. And they remind us that Earth is extraordinary. Not because planets are rare, we've found thousands of them, but because habitable, stable, long-lasting planets are rare, very rare. They force us to expand our understanding of what a planet can be, how it can behave, what conditions it can endure. And they remind us that Earth is extraordinarily rare. Not because planets are rare, we've found thousands of them, but because habitable, stable, long-lasting planets are rare, most worlds are extreme, most worlds are hostile, and that makes Earth even more precious. Earth isn't just in the habitable zone. It exists in a solar system that's been stable for over 4 billion years, long enough for life to arise. Long enough for that life to evolve from simple, single-celled organisms into the complex biosphere we see today. Long enough for intelligence to emerge. Our Sun is well behaved. It's a main sequence star, burning hydrogen in its core, producing steady, reliable energy. It doesn't flare like a red dwarf. It doesn't vary in brightness dramatically. It's been burning at roughly the same rate for 4.5 billion years, and it will continue for another 5 billion. This stability is crucial. If our Sun produced frequent superflares, Earth's atmosphere might have been stripped away early in its history. Life might never have had a chance to develop. If our Sun varied significantly in brightness, Earth's climate would be unstable. Periods of intense heat followed by periods of cold. Life would struggle to adapt. But our Sun is steady, reliable, predictable. It's a Goldilocks star. Not too hot, not too cold, not too variable, not too short-lived. Just right. And Earth's orbit is nearly circular. Our orbital eccentricity is only about 0.017. That means Earth's distance from the Sun varies by less than 2% over the course of a year, from roughly 91 million miles at perihelion to 94 million miles at aphelion. This keeps our climate relatively stable. We don't have extreme temperature swings between our closest and farthest points from the Sun. The seasons are caused by Earth's axial tilt, not orbital eccentricity. Summer happens when your hemisphere tilts toward the sun. Winter happens when it tilts away. This creates moderate, predictable seasons. If Earth had a highly eccentric orbit, like some exoplanets, we'd swing from scorching heat to freezing cold every year. The temperature difference would be enormous. Life might not be able to adapt to such rapid extremes. Agricultural civilizations certainly couldn't. You can't grow crops if the temperature varies by hundreds of degrees each year. Our circular orbit keeps things stable. We have a large moon that stabilizes our axial tilt. Earth's tilt is currently about 23.5 degrees. This gives us our moderate seasons. But without the moon, Earth's tilt would vary chaotically over tens of thousands of years. Computer simulations show this clearly. A moonless Earth's tilt could swing from 0 degrees to over 80 degrees. At 0 degrees tilt, there would be no seasons. The equator would be perpetually warm. The poles would be perpetually cold. At 80 degrees tilt, the poles would point almost directly at the sun. Each hemisphere would experience 6 months of continuous daylight, followed by 6 months of continuous darkness. The temperature swings would be catastrophic. The climate would be utterly unstable. Ice ages would come and go rapidly. Life might survive, but complex life, intelligent life, would struggle. The moon keeps our tilt stable. It's been doing this for over 4 billion years. Ever since the Theia impact created it, we have Jupiter in the outer solar system, and this matters more than you might think. Jupiter's massive gravity acts as a shield. It deflects many comets and asteroids that would otherwise hit Earth. When a comet from the outer solar system falls inward toward the Sun, it often passes near Jupiter first. Jupiter's gravity can deflect the comet, change its trajectory, send it back out to the outer solar system, or pull it into Jupiter itself. The comet fragments that hit Jupiter in 1994, the Shoemaker-Levy 9 impact, demonstrated this. 21 separate fragments crashed into Jupiter over several days. Each impact released energy equivalent to millions of nuclear bombs. If those fragments had hit Earth instead, the results would have been devastating. Global extinction event. But Jupiter took the hit. Not all comets and asteroids are deflected. Obviously, Earth has been hit by major impacts throughout its history. The one that killed the dinosaurs 66 million years ago was 6 to 9 miles across. It released energy equivalent to billions of nuclear bombs. It created a crater over 100 miles wide. It threw so much dust and debris into the atmosphere that sunlight was blocked for months. Global temperatures dropped. Photosynthesis stopped. Food chains collapsed. 75% of all species went extinct. But without Jupiter, impacts like this would be far more common. Maybe every few million years instead of every 100 million years. Complex life might never get established. Every time it started to diversify, another impact would wipe it out. Jupiter protects us. We have plate tectonics, which might be rarer than we thought. Earth's surface is divided into large plates of crust. These plates float on the semi-solid mantle beneath. Heat from Earth's core creates convection currents in the mantle. Hot material rises, cool material sinks. This drives the plates. They move slowly, a few centimeters per year, about as fast as your fingernails grow. But over millions of years, this movement reshapes continents. Mountains rise where plates collide. Ocean floor is created where plates pull apart. And critically, this movement drives the carbon cycle. When plates collide, one is pushed beneath the other in subduction. Carbonate rocks from the ocean floor are carried deep into the mantle. Carbon is removed from the atmosphere and ocean. Over millions of years, this carbon is released again through volcanic eruptions. The cycle continues, regulating Earth's climate. If too much carbon dioxide builds up, temperatures rise. Faster weathering of rocks removes carbon more quickly. Temperatures stabilize. If too little carbon dioxide remains, temperatures drop. Slower weathering allows carbon to accumulate. Temperatures rise again. It's a thermostat, operating on geological timescales, and it only works because of plate tectonics. Venus doesn't have plate tectonics. Its crust is rigid, unmoving. Carbon dioxide has built up in the atmosphere. The greenhouse effect is runaway. Surface temperature is over 800 degrees Fahrenheit, hot enough to melt lead. Mars doesn't have plate tectonics either. Its core has cooled. Its crust is solid. There's no carbon cycle. Carbon dioxide was lost to space or locked into rocks. The atmosphere thinned. Surface pressure dropped. Now Mars is frozen, with an atmosphere less than 1% as dense as Earth's. Earth might be unusual in maintaining active plate tectonics for billions of years. It requires the right planet size, large enough to retain heat, small enough that the crust can be broken into plates. It requires the right interior composition, enough radioactive elements to generate heat, enough water to lubricate the process. It requires the right timing. If Earth's core had cooled too quickly, plate tectonics would have stopped. All of these factors aligned on Earth, and they might be rare among rocky planets. We have a magnetic field that's protected our atmosphere for 4 billion years. Earth's magnetic field is generated by convection in the liquid iron outer core. As the iron moves, it carries electric charges. Moving charges create magnetic fields. The result is a planetary-scale dynamo, a magnetic field that extends tens of thousands of miles into space. This field forms a protective bubble called the magnetosphere. When charged particles from the Sun reach Earth, the solar wind, most are deflected by the magnetosphere. They flow around Earth harmlessly. Some particles are trapped in the Van Allen radiation belts, donut-shaped regions where charged particles spiral along magnetic field lines. Only a small fraction reach the upper atmosphere. When they do, they create the aurora, the northern and southern lights, beautiful displays of green, red, and blue light, caused by charged particles exciting atoms in the atmosphere. Without the magnetic field, the solar wind would hit Earth's atmosphere directly. Over millions of years, the solar wind would strip away the atmosphere, atom by atom, molecule by molecule. We know this happens because we've watched it happen to Mars. Mars once had a magnetic field. We can see evidence in ancient rocks, magnetized minerals that froze into place billions of years ago. But about 4 billion years ago, Mars's core cooled. Convection stopped. The magnetic field disappeared. Without protection, the solar wind began stripping away Mars's atmosphere. Over hundreds of millions of years, Mars lost most of its air. What remains is thin, cold, unable to support liquid water. Earth's core has stayed hot. Our magnetic field has persisted. Our atmosphere has been protected for 4 billion years, and it's still protecting us today. All of these factors matter. The right star, the right orbit, the right moon, the right neighbor planets, the right geology, the right magnetic field, the right timing, the right luck, all had to align for Earth to be habitable. And they did. When we look at exoplanets, we see what happens when these factors don't align, when planets migrate into hostile orbits, when stars are too active, when magnetic fields are absent, when impacts are too frequent, when time is too short. We see chaos. We see extremity. We see worlds where life as we know it cannot exist. And that's normal. That's what most planets are like. Earth is the exception. The rare, precious, extraordinarily fortunate exception. Its atmosphere was stripped away by solar wind. What's left is less than 1% of Earth's atmospheric pressure. Earth's magnetic field has protected our atmosphere for billions of years. All of these factors matter. The right star, the right orbit, the right moon, the right neighbor planets, the right internal geology, the right magnetic field. All together, creating a planet where life can arise and survive for billions of years. They're not guaranteed. Most planetary systems don't have all these favorable conditions. Most planets experience extreme conditions that would make life impossible or incredibly difficult. When we look at exoplanets, we're seeing what's normal in the universe. Extreme conditions, unstable systems, hostile environments. Planets being destroyed by their stars. Planets losing atmospheres. Planets bombarded by radiation. Planets with surfaces hot enough to melt rock. Planets drifting alone through interstellar space. These aren't rare exceptions. They're normal. This is what most planets are like. Earth is the exception. We're the unusual ones. We're the rare, calm planet in a galaxy full of chaos. The galaxy is full of nightmare worlds. And that makes Earth even more precious. We're not just lucky to be in the habitable zone. We're lucky to be in a stable system. Lucky to orbit a well-behaved star. Lucky to have a large, stabilizing moon. Lucky to have Jupiter protecting us. Lucky to have plate tectonics and a magnetic field. All of these factors had to line up, and they did. Right now, somewhere in the universe, glass is raining sideways at thousands of miles per hour on HD 1-89733b. Right now, Kelt 9b is losing millions of tons of atmosphere every second, slowly being torn apart by its star. Right now, WASP 12b is being devoured, its materials spiraling into its host star. Right now, lava oceans churn on worlds we'll never visit. Right now, rogue planets drift through darkness between stars, cold and alone. These worlds are out there. We've seen them. We've measured them. We know they exist. And there are billions more we haven't found yet. Worlds, even more extreme, even more bizarre, even more incompatible with everything we understand about how planets should work. The universe is stranger than we imagined. And as our telescopes improve, as we discover more exoplanets, we're going to find even stranger worlds. Planets that challenge our understanding in new ways. Planets that force us to ask new questions about how planetary systems form, how they evolve, what conditions are possible. Every discovery tells us something new about the universe. Every extreme exoplanet expands our knowledge. Even if they're hostile, even if we could never visit them, they teach us. They show us the diversity of worlds that exist. They reveal the creativity of cosmic processes. They demonstrate that the universe operates on principles far beyond human experience, and they make us appreciate Earth. Every time we discover a planet where the surface is hotter than the sun, or where glass rains sideways, or where the atmosphere is escaping into space, we're reminded of how fortunate we are. Earth has liquid water, a stable atmosphere, a protective magnetic field, moderate temperatures. These aren't guaranteed. They're the result of billions of years of stability in a universe that's mostly chaos. So the next time you look up at the night sky, remember what's out there. Remember that those stars host planets, and most of those planets are nothing like Earth. Most of them are extreme, hostile, terrifying. But knowing that makes Earth's calmness, Earth's stability, Earth's habitability all the more remarkable. We live on a rare world in a universe full of nightmare planets, and that's something worth appreciating. Thank you for joining me on this journey through some of the most extreme worlds ever discovered. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep dives into the cosmos. And remember, the universe is full of wonders, but it's also full of terrors. Planets so extreme they shouldn't exist. But they do exist. They're out there right now, and they're waiting to be discovered. Good night, and may you never take Earth's gentle climate for granted again.